Good afternoon everyone, Mr. Ish here. Thank you for joining me for today's video. It might be a rather long video, perhaps a little technical and difficult because we're talking about hyperbolic functions. Do not take this topic for granted because hyperbolic functions are generally considered a difficult topic to understand, and it will become quite commonly seen aspect as you get into calculus. What are exactly hyperbolic functions? Any of those functions where you've seen the following terms, e to the x or e to the minus x, they are hyperbolic functions in an equation or in a function form. These two are very commonly seen in hyperbolic functions, and hyperbolic functions are related to the trigonometric functions, as each of the six trigonometric functions that you are aware of, each of those will have its own corresponding hyperbolic function. For example, sine x, when you look at the hyperbolic version of this, you get sine hx. You see this letter h over here indicates a hyperbolic function. Likewise, as another example, if you have cosecant x, the hyperbolic version of that would be cosecant hx. So this h, be aware of it. It indicates that you are now dealing with a hyperbolic function. And just as trigonometric functions, the six basic trigonometric functions are related to the circle, hyperbolic functions are related to the hyperbola. But what does it mean when I say trigonometric functions are related to a circle? Yes, I've talked quite a bit about trigonometric functions, but I've never kind of spoken about that circular aspect of it. If you have a basic plot over here, or a xy axis, and we have something called a unit circle. The unit circle is derived from trigonometry. You have points over here 0, 1. You'll have 0, minus 1. You'll have 1, 0. And here you'll have minus 1, 0. But at any point on this, any of these points on these circles can be represented in a coordinate pair. For example, if you were to have this point over here, it could be hypothetically some number, any point. If it was like a comma b, if this point over here represented a comma b, you can find the six trigonometric functions of the a comma b. You can. And likewise, you can find radians and angles for all of these coordinates. You know sine of 1, 0 is equal to 0, but the cosine of 1, 0 is 1, because you know the x over here represents the cosine aspect, and whereas the y value represents the sine value. So for any point you have on a Cartesian coordinate system, x, y, you can easily calculate the six trigonometric functions very quickly. If you can refer back to one of my videos I presented before on the fundamentals of trigonometry. If you have a point like say minus 3, 2, you know minus 3, 2 is going to come right over here. All you got to do is connect it over here, draw a right triangle. You have a minus 3 over here, you have a 2 over here, and you just have to find this hypotenuse. 3 squared plus 4 squared is equal to c squared, which will be root 13. Now given all of these, and here's your reference angle, you can find all the six trigonometric functions. So this right here is a concept of unit circle. Just as the basic trigonometric functions are related to the unit circle, the hyperbolic functions are related to the hyperbola. You know what a basic hyperbola is, something like this, a hyperbolic graph. So hyperbolic functions are related to this kind of a curve. Trigonometric functions are related to the unit circle. Keep that in mind as we proceed through this video. It is important to be able to calculate basic hyperbolic functions from easy to hard. Now look over here at this calculator of mine. I have a scientific calculator, but at no area on this calculator am I seeing the hyperbolic function buttons. I have sine, cosine, and tangent. I have inverse sine, cosine, and tangent, but I do not have the sine h, cosine h, and the tan h version of these functions. It might be hidden somewhere here, but I haven't never found it. So for those calculators where you don't have those hyperbolic function buttons, something which would look like this, sine h or cosine h, then you got to start learning how to manually calculate some of these values. And the procedure for doing that is to know these two basic formulas. Sine h x. The hyperbolic sine h function is always equal to e to the power of x. Remember I said when you see these, you're thinking about hyperbolic functions, minus e to the minus x over 2. Likewise, hyperbolic cosine function, cosh x is equal to e to the x plus e to the minus x over 2. You can see the difference over here. Everything looks the same except for this minus and the plus. But now within this function formula, you can easily start calculating the values without having them explicitly present on your calculator. You will still need a calculator, scientific calculator, to actually run these through, but you don't explicitly need to have these buttons on your calculator to use these formulas. So I want to present some examples where I'll be using these formulas and you'll understand exactly what I'm talking about. If someone tells you to find this, sine h of x, but here x is represented by 0, how do you do it? Well, you look back to this formula over here, the sine hx. Wherever you have x, you put 0. So you're just going to run it through. You'll have e to the power of 0 minus e to the minus 0 over 2. Now the rest is basically simple algebra with a little bit of understanding of the logarithms and exponential base concepts. Anything to the power of 0 is 1. 1 minus 1 over 2. You get 0 over 2, and you know your answer is exactly 0. Easy question, but you had to know this formula to run it through, especially if you didn't have these buttons on your calculator. How about this? Sine h of 2. Well, wherever you have x, put 2. You'll have e to the power of 2 minus e to the power of minus 2 over 2. You're going to run it through with your scientific calculator. This now here is not too hard. You can always work on this minus part and work in this direction. I'll put 2 minus exponent, I'll hit shift e. I'll minus that, and then I'll add that to e to the power of 2, and then divided by 2, I get a 3.626. 3.626. So this here represents the answer of sine h, the hyperbolic sine function of 2, 3.626. We can run through some more examples just to show you some more of these types of questions that can show up. But again, you have to be aware of these two formulas, the sine hx and the cosine hx. Very important. They'll show up too frequently, actually, too commonly. How about cosine h of 1 over 2? Well, you're going to plug 1 or 2 in each of these x's here in the cosine hx formula. You can do e to the power of 1 over 2 plus e to the power of minus 1 over 2 all over 2. Now you got to bring your calculator and solve it. I'm going to use 0.5. 0.5 minus shift, I get 0.6 over here, and I'm adding it to 0.5 shift e divided by 2. I'm getting a 1.127. 1.127. Easy. I'm hoping I'm not making silly mistakes over here. 0.5 minus, and you know you're hitting shift the natural log, because a shift natural log has the e to the x function. Then you add it to 0.5 shift natural log to get the e to the x. You get a value over here, 2.255. You divide it by 2 and you get 1.127. Looks right to me. Let's try another example. Slightly more tricky. Cosine h natural log 2. Now we have a little bit of a complication. Only complication because we're dealing with a natural log. I'm going to just erase this over here for neatness purposes, so everything doesn't look too jumbled up. Because all you gotta do is put it into the formula, e to the power of ln2 plus e to the power of minus ln2 divided by 2. The only problem which may arise here is the fact that we can make a silly mistake just using the calculator. I want to hit 2 and natural log it. And before I do that, this is the button I'm talking about on my calculator. It looks like this, natural log, but on top I have an e to the x. And to access this e to the x, you always have to shift. You hit shift and then the natural log, it accesses that function on the top. But like I was saying, the common issue we can have here is just a simple mistake using the calculator. I want to do a natural log 2. I get 0.619. I want to save that because I'm going to work from this direction that way. So I'm going to hit my memory recall. I have a 0.693, but I'm going to minus it because I have a minus. Then I'm going to hit shift natural log. I get a 0.5 plus memory recall and shift that natural log 2. I get a 2.5 on the top, and you divide it by 2 and you get a 1.25 as your answer. 1.25 as my answer. So that's pretty much this basic hyperbolic stuff. As we keep proceeding through this video, things are going to get slightly harder. I have rearranged the board a little bit for space because some of these questions we look at next will require a bit more space. They may not really require a calculator, but they'll be more of proving and identities. I have these basic function formulas right over here, we'll need them. But here's a question. Cosine hx minus the hyperbolic sine hx is equal to e to the minus x. You have to prove that this right here is equal to e to the minus x. It's simple because all you have to do is plug these formulas exactly where they will belong. Cosine hx, you know, is going to be e to the x plus e to the minus x over 2, and you're minusing from this the sine hx formula, which is e to the x minus e to the minus x over 2. It should all equal e to the minus x. We'll see that as well. You got to open, you have to, well, eliminate the parentheses, but we can do several steps here together. Let's put a common denominator. 2 and 2, the denominator is 2. 2 goes in here 1 time, so all of this on the top stays the same. E to the x plus e to the minus x. Now we got a minus over here. 2 goes in this 2 1 time. All of this will stay the same, except you'll get, each of these items will get hit with this minus sign. You get minus e to the x. This minus will hit with that minus, give you a plus e to the minus x. And it should equal e to the minus x. The fun part is always when you have something which looks tricky and you start cancelling things out. You have e to the x here and a minus e to the x, they cancel out. You have e to the minus x and e to the minus x, they're like terms, combine them. You get 2e to the minus x divided by 2. The 2's cancel out and you get left with just e to the minus x. So this is just one of those questions which requires algebra, but it also requires you knowing how to use these formulas to prove something. I want to present some more such types of questions. Here is something to show. Remember, many of these identities are very similar to the ones in trigonometry, those basic fundamental trigonometry identities. We want to show that this right here, the minus x of this hyperbolic sine function, will actually equal that. So you want to start by writing your formula. E to the x minus e to the minus x over 2. But what here is exactly representative of this x value? It's actually minus x. So this minus x must replace these x's. So we will do that. You have e to the minus x because our function here, input is minus x, not regular x. Minus e to the minus x over 2. Open this part up. What do you get? E to the minus x minus e to the x over 2. You see, we're getting this. E to the minus x minus e to the x is divided by 2. Let's hit everything over here on the top by minus 1. Minus 1. Hit everything on the top by minus 1 to get things reversed. What do we get? Positive e to the x minus e to the minus x over 2. Right? I have done that to flip these things around. Why did I flip them around? Because I'm trying to prove that this is equal to sine hx. The minus version over here makes it minus sine hx. And this minus here representative of this minus 1. But look what I have over here. It looks awfully close to what we have here. E to the x minus e to the minus x over 2. It is exactly the same. Except what we had to use was a minus 1. So it goes to show that hyperbolic sine of minus x is equal to minus sine hx. I hope you saw that. The minus 1 employed to prove this specific identity. And we can do the same thing with the cosine h. Look over here. Cosine h, hyperbolic of cosine function minus x should give you a positive cosine hx. Remember, sines are origin symmetry, odd functions. Cosines are y-axis symmetry. I'm talking about the basic trigonometric version of these functions. This is usually even function. And even functions remain positive even when you get hit with the minus input. Again, write the formula over here. E to the x plus e to the minus x over 2. But you got to put in the input minus x in place of x. You have e to the minus x plus e to the minus x, because our input is a minus x over 2. Open this part on the top, we get e to the minus x plus e to the x over 2. Look over here, everything is positive. The exponents are minus and plus, however they are. But look at it, it looks exactly like this, except things are just reversed around. You don't even need to hit anything with a minus 1. You can just write this first and this second, and you get e to the x plus e to the minus x over 2, which is equal to cosine of hx, because this right here is represented by this exact same formula. So the minus input of a hyperbolic cosine function is the same thing as the positive input of the hyperbolic cosine function. So you have proven this identity. I want to present some more proofs, but slightly more difficult than this. Take a look at this hyperbolic function identity. It looks very close to the one you saw for sine. Sine 2 theta is equal to 2 sine theta cosine theta, except here we're dealing with hyperbolic functions. We want to prove that this is actually equal to this. And it shouldn't be too hard. The goal over here, the trick over here is to work on both sides simultaneously. You know sine h2x is the same thing as saying sine hx plus x. And you know here's the sum formula for sine. You can write this out as 2 sine hx and cosine hx. You can still keep this unchanged. You know this over here is going to be sine hx cosine hx plus sine hx cosine hx. Wanted, right? Let's show you that. It's going to be sine hx cosine hx plus sine hx plus, well, not plus, it's multiplying over here, cosine hx, which should equal to exactly what you're seeing, 2 sine hx cosine hx. But what exactly does this represent in terms of an actual answer? We can start using these over here. You know sine hx is what? E to the x minus e to the minus x over 2. And you know it's multiplying with cosine hx, which is what? E to the x plus e to the minus x over 2. Multiply this out. Think of this as you're looking at it on the top only. A minus b times a plus b, and do your multiplying. You're going to get, this is going to multiply with this, and this is going to multiply with that. And these inner items will multiply with those. Just like the FOIL method. You can get e to the 2x. This will multiply with this to give you plus e to the x and e to the minus x. These inner two items will give you minus e to the x and e to the minus x. And this with that will give you minus e to the minus 2x over 2 times 2, which is a 4. You can cancel stuff out. This over here can cancel out with that. You can cancel it. This 2 can cancel with this 4 and give you a 2. You have e to the 2x minus e to the minus 2x. What is that? E to the 2x minus e to the minus 2x over 2. You're seeing that? E to the 2x minus e to the minus 2x over 2. Maybe we can do something over here. We can bring them together as e to the 2x minus 1 over e to the 2x all over 2, and everything here is with the denominator. Your denominator here is e to the 2x. Everything is again over 2. 1 goes in e to the 2x, e to the 2x times. It multiplies with that to give you e to the 4x. E to the 2x goes in this 1 time minus 1. Right? You can flip everything around because this is a 2 or 1. You'll get e to the 4x minus 1 over 2e to the 2x. You can say all of this can be represented with that answer. But our goal was here just to show that this was actually equal to that, and we did. But you can see how sometimes things can get a little complicated when you start running through these. In this question over here, I want to show you that the cosine h square x minus sine h square x equal to 1. I want to show it out mathematically why this part here will end up being 1. And it's simple. You just have to plug in these formulas and work with them. Cosine h formula, you know, is there. You have e to the x plus e to the minus x over 2. But all of this is squaring because, you know, you have a square over here. And you got to do the same thing with this sine hx formula. E to the x minus e to the minus x. These x's can sometimes be a little messy to write. And you got to square it is equal to 1. The tough part here is just opening all of this up because it can become pretty long sometimes. Let's do that. We'll look at here at the top part. E to the x plus e to the minus x times same thing. You'll get e to the 2x. You'll get plus 2e to the x, e to the minus x. Remember, I'm doing this in my head. And you'll get plus e to the minus 2x over 4. You got to minus this from what you'll get over here. Because if we have a minus, we should put a parentheses. You'll get e to the x minus e to the minus x times, again, the same item. You'll get e to the 2x minus 2e to the x, e to the minus x. These right here are your intermediate terms. Remember, a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. And here you get plus e to the minus 2x over 4. Common denominator, 4. open everything on the top because it's all part of the same line now. But as we open them up, let's cancel things out. This e to the x is going to get hit with this minus e to the 2x and they'll cancel out. This plus e to the minus 2x will get hit with this minus e to the minus 2x and they'll cancel out. What you'll only be left with are these intermediate terms. This intermediate term will become a plus because minus times minus will become plus. You'll get 2e to the x, e to the minus x, plus 2e to the x, e to the minus x over 4. You gotta just simplify all of this. Look at these. These are basically what? E to the x times e to the minus x. You have an exponent multiplying by its reciprocal. Look over here. A to the square times a to the minus 2 is the same thing as a to the 2 plus minus 2, which is what? A to the 0, which is 1. So each of these over here cancels out into a 1. So you get left with a 4 over 4, which is just a 1, and we've shown you that 1. So remember that little shortcut over there. Anytime you see something like an e to the x multiplied by e to the minus x, you're basically just going to equal this to a 1. You can also look at it as e to the x over e to the x. Why? Because this minus exponent here refers to a minus, a reciprocal, a 1 over, right? So it all cancels out and gives you that 1. So you can do these shortcuts. Sometimes when you have different types of identities, they can get quite complicated, but other than just a space issue, you can still run them through and you'll get still the right answer. Let's shift gears a bit and look at something beyond sine and cosine. Principles will still be the same. Hyperbolic tangent function of 0. How we do it? Think about what tan really is. It's a sine h over cosine h. Right? Isn't tangent equal to sine or cosine? Now you gotta individually run these through the formula. E to the 0 minus e to the minus 0 over 2. This right here covers the sine h 0 aspect. Now we go to the cosine version. E to the 0 plus e to the minus 0 over 2. What are we going to get? This is a 1 minus 1 over 2. You're going to get a 0 on the top. You get a 1 plus 1, 1 over 2. So all of this will still end up giving you exactly 0. But you can see some of these functions which you'll see other than sine h cosine will rely on the same principles that you will see in the basic trigonometry questions. You just have to remember what their function actually means. How about this one right over here? The question is this: hyperbolic of cotangent, cot h, 1 over 2. You know cotan is cosine over sine, but in terms of hyperbolic functions, it's cosine h or sine h. Of course, each with a 1 over 2. Run it through the formulas. E to the power of 1 over 2 plus e to the power of minus 1 over 2 over 2. This right here is your cosine h, hyperbolic cosine. Let's do the hyperbolic sine. You'll have e to the 1 over 2 minus e to the minus 1 over 2 over 2. Now, look over here. These two denominators are the same. When you flip things around, they'll cancel out anyway. So just don't waste time and cancel them out right away. You have this numerator and this new denominator. Run this through to the calculator. The only mistake we can make here is not a silly mistake. I'll do the denominator first. I'll do 0.5 minus shift of natural log to get that. I'll add that to the 0.5 and shift it again. On the bottom I get a 1.042. 1.042. Assuming there's no silly mistake being made here. Now let's do the top part. 0.5 minus shift natural log to get that exponential function kicking in. Add that to 0.5 and shift it again. You get a 2.55 on the top. 2.55. 2.255. Complete this out. Divide it by 1.042 and your final answer is a 2.16. 2.16. The most difficult aspect of this question is the actual calculating part. But opening it up into your basic expression is not hard. It relies very much on trigonometry fundamentals. Look at this question right here. How about we make it interesting, make it natural log 2. Natural log 2. We're talking about cosecant, hyperbolic cosecant function, natural log 2. You're going to look at this one over here, but you know cosecant is the reciprocal of sine. So you're going to do 1 over sine h. natural log 2, which represents your x, your input. You're going to put everything into this formula, but with a 1 over e to the natural log 2 minus e to the minus natural log 2 over 2. Flip everything around. What do you get? You get 2 over e to the natural log 2 minus e to the minus natural log 2. Again, now the most difficult part is not to make a calculator mistake. Do natural log 2 and save it in your calculator. Natural log 2 and save it as your memory recall. And then work from this direction that way. I'm going to hit my memory recall. I'm going to put a minus over here. I'm going to do shift natural log. I'll get this equal to a 0.5, but it should be a minus 0.5. I'll hit a minus on that. Then I'll hit that with the memory recall and shift E. And here on the bottom I get a 1.5. Total 1.5. So 2 divided by 1.5 gives me a 1.33, which is a 4 over 3. And 4 over 3, 100% is your right answer. 4 over 3. The answer to this question here is 4 over 3. Let's look at another one of these type of questions, and we'll shift gears again into looking at some identities which will involve something more complicated than just sine and cosine. The question is this. Secant. Hyperbolic secant function. Put a 1 over 2 over here. You know this is a 1 over cosine h. Hyperbolic cosine of 1 over 2. Your input value 1 over 2. Write it out as this. In this formula with the 1 over 2 plugged in place of x plus e to the minus 1 over 2 divided by 2. When you flip this around, you'll get 2 over e to the 1 over 2 plus e to the minus 1 over 2. Calculator again. I'm going to do 0.5, save it in my memory. Why am I doing saving it in my memory? Because it just makes the whole process convenient. I'm going to work from this direction, from the right to the left. You can work in whichever direction, but I'm going to do it that way. Memory recall 0.5, I'm going to minus it and shift natural log. I'll get a 0.606, but I'll add this to my memory recall 0.5 shift E. I get a 2.255 on the bottom. I can do the reciprocal right over here and multiply it by 2, and I get a 0.8868. 0.8868. Remember, you all can calculate this your own way, but the main thing is do not make a silly mistake and condemn your answer simply because you calculated things improperly. Now for some of these questions we'll look at next, identities. It'll get a little bit more involved. Our identity is to show that 1 minus tan h square x is equal to secant square h. You know, you have a similar identity in trigonometry. 1 plus tan square x is equal to secant square x, but we have to show this, the hyperbolic versions. Might be a little tricky, but I would say outright work on both sides simultaneously, and let's start putting in our functions over here. You know, 1 minus tan h square x is going to be sine h square x over cosine h square x, which is equal to 1 over cosine h square. I'm missing an x over here, aren't I? Right? Kind of confused me there for a little while. Now plug in these formulas right here in place of the appropriate areas. We have 1 minus e to the x minus e to the minus x over 2 all square. Now we're looking at the cosine h square part, aren't we? E to the x plus e to the minus x over 2 whole square. Let me improve the appearance of this 1 minus, because it's not minusing from the numerator, it's minusing here from the side, from the whole thing. Let's put the cosine h, hyperbolic cosine function here, e to the x plus e to the minus x over 2. Remember I was saying earlier, sometimes these things can get messy, it can get big. Now you gotta individually solve these. Let's put this. We gotta multiply this with itself twice. Easy, but can get complicated at times. You'll have e to the 2x. You'll have minus 2e to the x, e to the minus x. I'm doing this in my head over here. Plus e to the minus 2x over 4. 2 squares of 4. Now we're looking at the cosine part. This whole thing multiplied by this whole thing. Okay? You'll add e to the 2x. I was struggling here a little bit with that x. Plus 2e to the x, e to the minus x. Plus e to the minus 2x over 4. As I said, these things can get a little messy. Is equal to all of this. You got to open it up, don't you? You have e to the 2x plus 2e to the x, e to the minus x plus e to the minus 2x over 4. Similar denominators, cancel them out. Look over here, you have e to the x times e to the minus x, a power multiplying by its reciprocal. They'll cancel out and give you just 1, won't they, right? So you can actually remove this and just leave a 2, because 2 will hit with that 1 to retain the 2. And again over here, you can erase this part over here because it'll just stay as a 2. And look over here, the same thing. A base with a power multiplying with the same base and its reciprocal, it'll become a 1 over here. I'm doing all of this little cancelling out to avoid getting too messy over here. So this is what I'm left with. But here I still have to do a common denominator over here. In the interest of space, that we have limited space, let's start working over here. The common denominator is going to involve this and 1. And of course this will prevail in that fight over there. You'll have e to the 2x plus 2 plus e to the minus 2x. 1 will go in all of this the same number of times. You'll have e to the 2x plus 2 plus e to the minus 2x. But it's minusing over here now with all of this. I'm going to write these terms here, but with the impact of that minus sign, you'll get minus e to the 2x. Minus will hit with this, minus will give you that plus 2. Minus will hit with this e to the minus 2x to give you minus e to the minus 2x. And you know you gotta still be looking over here. Flip it around. It's gonna flip. You get 4 over e to the 2x plus 2 plus e to the minus 2x. We're getting a little messy over here, aren't we? But now, easy part. We can cancel things out. This cancels out. This cancels out. E to the minus 2x cancels out. That cancels out. What do we got left with on the top? 2 plus 2, 4. 4 over e to the 2x plus 2 plus e to the minus 2x is equal to, same, 4 over e to the 2x plus 2 plus e to the minus 2x. Yes, it can get a little messy. Yes, it can get a little tricky, but it's not too hard. And we proved that this expression over here was equal to this expression over here because you at the end ended up getting the same thing on the left equaling the same thing on the right. So we proved that this identity over here is good. Remember in the trigonometric version it's tan square x plus 1 equals secant square x, but when you do the hyperbolic version you get a 1 minus tan square hx is equal to secant square hx. A very useful identity that play up in calculus. I want to look at some more. Here is another question. The hyperbolic cotangent square x minus 1 is equal to hyperbolic cosecant square x. Similar to what we saw in trigonometry, but there was a cotan square x plus 1 equals cosecant square x. But here we have a little bit of a minus 1 playing in. We just want to prove that this is equal to this. Not too hard, but it'll be a little elaborate. It'll take space. You want to start again by plugging in. I erase those over here just to create space. You know this is going to be cosine h square x or sine h square x minus 1. This is 1 over 1 is equal to 1 over sine h square x. Now start plugging away over here. You can have e to the x plus e to the minus x over 2 square. This is my cosine h square playing over there. Now this will be e to the x minus e to the minus x over 2 square minus 1 over 1 is equal to 1 over e to the x minus e to the minus x over 2 square. Let's come down right here. Open this top part up. You can get e to the 2x plus 2e to the x e to the minus x plus e to the minus 2x over 4. And the denominator over here will be e to the 2x minus 2e to the x e to the minus x plus e to the minus 2x over 4. Why you get a minus 2 here and a plus 2 here is because this. You have a minus here and a plus over here. When you open them up, you'll automatically get that. Minus 1 over 1 is equal to 1 over e to the 2x minus 2e to the x e to the minus x plus e to the minus 2x over 2. I want to do some simplifying over here. E to the x multiplied by its reciprocal, this will cancel out to just give you 2's. Same here, cancelling out here, same here, cancelling out. You want to do a common denominator, but this 4 and this 4 will cancel out. This right here has become your new denominator. This right here is your numerator. You're going to minus with 1 over 1 and see if you end up with that. Let's write over here our new common denominator. The new common denominator is between this arrow and this 1, and this will be your denominator. It will be e to the 2x minus 2 plus e to the minus 2x. Let's erase this here for space. This goes in all of this the same number of times, so this numerator will end up back over here. E to the 2x plus 2 plus e to the minus 2x. Now 1 goes in this that many times, but it will multiply with 1 to start adding you those values over here, but in a minus version. See, 1 will go in this these many times, and these many times will multiply with this numerator, and that will be impacted with this minus sign. So I'm going to put all of these values as they are impacted. You get e to the 2x. This minus 2 will become a plus 2. This plus e to the minus 2x will become minus e to the minus 2x. And you know this should equal the flip of this. And I made a little thing over here, error over here. This is a 2 over here. But when I open it up, it should become a 4 over here. So you'll get a 4 over e to the 2x minus 2 plus e to the minus 2x. Yes, it gets a little messy. It gets a little confusing. Now the fun part, cancelling. This cancels out with that, that with that. You get 4 on the top. 4 over e to the 2x minus 2 plus e to the minus 2x is equal to 4 over e to the 2x minus 2 plus e to the minus 2x. So we show that it is indeed true. I understand that this board can get messy and the writing can get messy, but you have the advantage here with your video. You can pause it and you can look at it, and you don't have to chase time or speed your way through it. You can just look at it. Just take a still of this and you can look at it. It's all worked out. I want to present at least 2 more such examples. I want you all to focus in on this question. It'll be a little tricky, but not too hard. 1 plus tan hx divided by 1 minus tan hx equals e to the 2x. We have to show that this expression here equals e to the 2x. For this type of question, it's easy to just carry it out using techniques without complicating your question, and this is what I mean. Convert everything into its base functions. You know tangent is sine over cosine, so do that. Don't start bringing in the definitions right away. You can bring the definitions, but again, do not advise you to do that. Carry this technique out as far as you can till you can finalize it, and then bring those definitions in. And you know what I mean by the definitions. I'll show you momentarily. Common denominator here will be cosine hx. 1 goes in this cosine hx times, right? Plus sine hx. Common denominator here on the bottom is a cosine hx. 1 goes in that, of course, cosine hx times minus sine hx. You can easily cancel this denominator with this denominator, and what do you get? You get cosine hx plus sine hx divided by cosine hx minus sine hx. Now bring in your definitions. Had you brought in your definitions over here, you'd be running through all of that mess. Bring them in now. You'll get e to the x plus e to the minus x over 2 plus e to the x minus e to the minus x over 2. This is our top part. Lower part, e to the x plus e to the minus x over 2 minus e to the x minus e to the minus x over 2. Come up over here. You have a common denominator over here. So just extend this line across and bring them under a single 2, because they're both the same things. Look over here, you have a common denominator here too. Bring them across a single thing, but you have to be careful here because we're involving a minus. You see we have a minus over here. This minus would have impacted this minus and given you a positive. Had you not done this shortcut here, you would have gone that positive. But look over here, common denominators too will cancel out. Now all you gotta do is things you can cancel out. You gotta look for those things. You have e to the positive e to the minus x and minus e to the minus x. These can cancel out. It's like saying 1 minus 1 is 0. And look over here, plus e to the minus x and plus e to the minus x, they don't cancel out. But what cancels out here? E to the x and minus e to the x. In essence, you get on the top 2e to the x. Let's be a little neater. 2e to the x divided by, what did we get over here? 2e to the minus x. Cancel out the 2's. We have e to the x divided by e to the minus x. Properties of exponents becomes e to the x. Bring it up. Plus x e to the 2x. And we are done. Remember, this right here is a tricky part, because this e to the minus x can be viewed as this, e to the x divided by 1 over e to the x. When you flip this around, it comes out hitting this with the times. And you know, when you're multiplying exponents with the same base, you add them up. Hence, you get this e to the 2x, and you're done. I'll present another question similar to this, slightly more complicated. I hope you'll enjoy that question. So let's focus in on this question. Tan h natural log x is equal to x squared minus 1 over x squared plus 1. You have to show that this is equal to that. You're going to, in this question, end up with both of these scenarios where e to the power of ln x and e to the minus ln x must equal something. And that comes from one of the identities I presented to you in the properties of logarithms video. We know this one right here on the top equals x. But just as a quick refresher, if you want to solve for it, you know this is equal, y is equal to this and y is equal to that, f of x and f of x. If y is equal to e to the power of ln x, you bring the exponent as a coefficient, you do a natural log, right? Natural log y is equal to a natural log x, natural log e. This zeroes out as a 1. Bring everything to one side of the equation. Ln x minus ln y is equal to 0. Ln x over y is equal to 0. You take the natural log on the other side, x over y is equal to e to the 0, which is equal to 1. Therefore, y is equal to x. So you know this right here, when you see e to the ln x, you should be thinking x. When you see e to the ln x, you should be substituting it with an x. But let's look over here. Do the exact same thing. Bring the exponent as a coefficient. Natural log y is equal to minus natural log x, natural log e. Natural log e is always equal to 1. Take everything on one side. Minus natural log x minus natural log y is equal to 0. Isolate minus natural log x plus natural log y is equal to 0. You can essentially take the minus on the other side and eliminate it, because 0 divided by minus 1 is a 0. Properties of logarithms, when they're adding, they're multiplying. Ln xy is equal to 0. Take the natural log on the other side. Xy is equal to e to the 0, which is equal to 1. So what is x is equal to here? Or should I say rather, what is y equal to here? Y is equal to 1 over x. So when you see e to the power of minus ln x, you should be putting 1 over x. And these substitutions will come in for this question. Now all I gotta do is actually make space so I can run this through. And I've shown you why these substitutions will play in right over here. Let's make that space. Proceed with this question as if you were doing a regular question where you're splitting the tangent into the sine and cosine components. You get a sine h natural log x over cosine h natural log x. Anyhow, bring in the definitions over here. You have e to the natural log x minus e to the minus natural log x. Remember, it's e to the x minus e to the minus x over 2, right? For the sine h, the hyperbolic sine, and the hyperbolic cosine is e to the x plus e to the minus x over 2. Except here x is replaced by ln x's. E to the ln x plus e to the minus ln x over 2. Cancel out these 2's because they'll cancel out anyways. What do you get? E to the ln x minus e to the minus ln x divided by e to the ln x plus e to the minus ln x. Now this is where the wonderful substitutions will kick in. E to the ln x was equal to x. E to the ln x was equal to x, because we showed you that whole expression here was equal to x minus 1 over x. Divided by e to the ln x was what? X plus 1 over x. Now it's just a matter of simple fraction algebra to get this answer here. On the top we have a denominator of x. 1 goes in x times, so you have x squared minus 1. On the bottom you have a denominator again of x, right? 1 goes in x times, you get x squared plus 1. Cancel out these x's, what do you get? X squared minus 1 over x squared plus 1. And our answer is shown. It's done. The most difficult part of this question entirely was not this part right here, it was this right here, to show you that this can be simplified by means of a property or identity into its easier components. I want to shift gears here and show you how we can work backwards with hyperbolic equations. It's important to know that, especially if your calculator does not have the hyperbolic function on it. Very important to know that. So here's a challenge. If someone told you to find the hyperbolic cosine function of 2, and you would get at 3.762, and you'd get at it by using the basic definition of the hyperbolic cosine function to be this, you'd be plugging in places of x, the 2, you can easily get this, right? This is like the type of example I showed you at the beginning of the video. But what if the question was this? Cosine h of some x value is equal to 3.762. And without your calculator having the hyperbolic function, how would you determine that the hyperbolic cosine function of that specific angle gave you 3.762? So how would you actually work backwards? That is the question over here. So x here would be equal to cosine h inverse of 3.762. But how would you actually work this out? This is exactly how you would do it. Of course, you have to be given the answer, but you have to determine what value gave you that answer. So you're working backwards. This is where some quadratics will come into play. You would start with the basic definition of the cosine function. E to the x, the cosine hyperbolic function, plus e to the minus x over 2 is equal to 3.762. Take 2 on the other side. We need our calculator over here. So you're going to get e to the x plus e to the minus x is equal to, let's get some numbers there, 3.762 times 2, I get a 7.524. Simplify this part. I don't like the negative exponent. I have e to the x plus 1 over e to the x. Remember, negative exponent is equivalent to the reciprocal of it. Common denominator here, e to the x. 1 goes in e to the x times it multiplies with this value right here to give you e to the 2x. Plus 1 is equal to 7.524. Multiply this across. You get e to the 2x plus 1. I gotta write this in a better way because it's not an exponent. Plus 1 is equal to 7.524 e to the x. Bring everything on one side. E to the 2x minus 7.524 e to the x plus 1 equals 0. A quadratic function is coming into view here. Quadratic formula will play in. What's my a value? It's 1. What's my b value? Minus 7.524. You all know the quadratic formula is c is 1. Minus b plus minus square root of b squared minus 4ac over 2a. You gotta plug them in. You'll get a positive 7.524 plus minus b squared 7.524 square minus 4ac will give you a minus 4 all divided by 2. Right? You could have done a substitution technique over here where you say u is equal to e to the x. You could have converted all this into u square minus 7.524u plus 1. I'm only showing you this part over here in case you couldn't visualize this in your head. You could have done this technique. Let's calculate this to get our two answers. I'm going to work from radical outwards. I have 7.524 and I square it. And then minus 4 from it, then I square root it. And I'm going to save that answer. I'm going to present you two solutions because you have a plus and a minus. 7.524 minus that divided by 2, I get a 0.1353, and my other solution involving the plussing, 7.524 plus, and divided by 2, I get a 7.388. But supposedly u is equal to all of this, e to the x is equal to that, x is equal to the natural log of that. Take 7, look over here, e is equal to the natural log. E is equal to natural log of 7.3888. I'm only using 7.3888 because it will give you your answer. I natural log it, I get 1.9999 simply because I don't have all the numbers written here. I'm not getting a 100% accurate answer, but I'm getting very close. It's equal to 2. So the ability to work backwards almost always involves the application of the quadratic formula, and you will use the substitution technique. Just remember at the very end, you resubstitute back and you do your natural log. So here's a rather interesting question the hyperbolic cosecant function of x should equal to 0.3. This is one of those inverse hyperbolic procedures where you are trying to determine the value such that if you were to take the hyperbolic cosecant function, you get a 0.3. You can rewrite all of this such as this. Cosecant h minus 1 of 0.3 should give you that value that you're looking for. You want to try to go in the normal course of manner here, such that you're trying to keep your whole process easy. Look over here, convert this into the reciprocal function, identity function, and make it equal to 0.3. You know what the sine hx is equal to? You know sine hx, well, let's just put it over here, e to the x minus e to the minus x over 2. All of this in the reciprocal format is equal to 0.3. You gotta flip this part around over here. You get 2 over e to the x minus e to the minus x. See, I flipped this, is equal to 0.3. Take this entire expression, multiply it there with the numerator. 2 is equal to 0.3 e to the x minus 0.3 e to the minus x. You got a fraction over here actually. 2 is equal to 0.3 e to the x minus 0.3 over e to the x. This of course is an over 1. Common denominator, e to the x. 1 goes in e to the x times, multiply with this numerator. You get 0.3 e to the 2x. Let's bring this over here too, carrying it down. Minus 0.3, because this goes in there 1 times 0.3 is a 0.3. Take this on the other side. You know it's a process. 2e to the x is equal to 0.3 e to the 2x minus 0.3. Quadratic equation is in the works here. Rewrite it out. So bring everything onto one side. 0.3 e to the 2x minus 2e to the x minus 0.3 is equal to 0. Quadratic equation, ax squared bx c. Quadratic formula will apply over here. A, b, c. 0.3 is my a value. B minus 2, c minus 0.3. Look over here, substitution. Let u equals e to the x. Therefore, all of this is 0.3 u squared minus 2u minus 0.3 equals 0. Now we're actually solving for u. U is equal to the quadratic formula. Let's plug in the values. You get a minus b becomes a plus 2. B squared becomes a 4. Minus 4 times a, 0.3 times c minus 0.3. All divided by 2a, which is 0.6. 2 times 0.3 is a 0.6. You're solving here for u. U is going to give you two values. You get a positive value and a minus value. I'm going to throw the minus value. Why? Because when I put the minus value and I solve for x, I'm going to do a natural log of a minus value. You don't want to do a natural log, so you'll throw the minus. We're essentially focusing here on the positive value, the 2 plus onward. Let's calculate the positive value here. You're going to do all of this. 4 times 0.3 times 0.3 minus plus 4, square root it. Add that with a plus 2, divided by 0.6. What I get is 6.813. U is equal to 6.813. If you were calculating the minus answer, you would be getting I believe, a minus 0.1467. We'll throw this out because e to the x, which is equal to u, is equal to all of that. You can't do negative logs, but you can do this. X is equal to a natural log of 6.813. X is equal to a natural log of 6.813. You do natural log of that, you get 1.9188. 1.9188 is your answer. The hyperbolic cosine of 1.9188 equals 0.3. How do you actually check your answer? Well, it's rather easy but elaborate. You would basically look over here. Let's look down over here actually. You know your basic sine formula is right over here. E to the x minus e to the minus x over 2. Wherever you have this x, you'll put that 1.9188. But you know this is for the sine hx, right? Would equal to that. But we have to find the cosecant hx. Could the cosecant hx would equal to 1 over all of this with the plugged in values, e to the power of 1.91888 minus e to the power of minus 1.9188, all divided by 2. If you mathematically, by means of your calculator, solve this out, you'll get a 0.3. And I think I'll solve it out. I'm going to save this 1.9188 in my memory, and I'm going to work from right towards the left. I take my memory recall, minus it, and shift E, then I minus that from this first part. I get a 6.66659 divided by 2, but I have to take the reciprocal of this, and when I do that I get a 0.3. See, I get a 0.3. So this answer over here is good. So you can see, again, an elaborate process involving the quadratic formula. Can be tricky, can be messy, but at the end when you get the right answer, it's actually fun. Here's how the questions will normally show up. Essentially, you're saying that you're finding the hyperbolic tangent of a certain value for which you got the answer 0.5. The question is this, but you're reading it this way. What's sine hx? E to the x minus e to the minus x over 2 divided by, what's cosine hx? E to the x plus e to the minus x over 2 is equal to 0.5. Cancel these 2's out. One of the best things you can do is just cancel them out. You get e to the x minus e to the minus x over e to the x plus e to the minus x is equal to 0.5. Take this entire expression and multiply it up over here. You'll get e to the x minus e to the minus x is equal to 0.5 e to the x plus 0.5 e to the minus x. Bring everything on one side. What do you get? You bring them over here, you get e to the x minus 0.5 e to the x. You get 0.5 e to the x. Minus e to the minus x minus that, well, you get minus 1.5 e to the minus x is equal to 0. Common denominator over here, after you convert into a fractional form. Minus 1.5 over e to the minus x equals 0. Let's shift over here for space. And this should have become a positive, because if I'm bringing a minus exponent down, it becomes positive. My denominator here is e to the x. 1 goes in e to the x times, which multiplies with this to give you 0.5 e to the 2x minus 1.5 equals 0. Take the e to the 2x on the other side, multiply it by 0 and it disappears. You get 0.5 e to the 2x minus 1.5 equals 0, but take the 1.5 on the other side, you get equals 1.5. Get rid of these coefficients. E to the 2x is equal to 1.5 divided by 0.5, which is a 3. Simple logarithm part over here. Get rid of the exponent. 2x natural log e is equal to natural log 3. This is a 1. X is equal to natural log 3 over 2. But we need to present an answer here. Let's do it. 3 natural log divided by 2, I get a 0.5. X is equal to 0.5493. We need to just check basically to see if our answer indeed is true. To actually check your answer for something like this, which is slightly more involved because the tan h is actually sine h or cosine hx, you have to actually plug this into this formula right over here and work. Or you can even plug it into this over here. But look what happens. I'm going to look at this formula right here. E to the power of 0.5493 minus e to the minus 0.5493 over 2. This is the sine hx, the hyperbolic sine. Now look at the hyperbolic cosine. You plug in the same value, your answer you got. Plus e to the minus 0.5493 over 2. These over 2's can cancel out. So essentially you're solving this part on the top and dividing by this part on the bottom, and using the 0.5493 value you should get a 0.5. I want to do that because I want to show you that the process we employed here was true. Let's use a 0.5493 minus, and I'm going to run through this fast, plus 0.5493, shift that. On the denominator I get 2.309, I'm going to save that. I'm going to look at the numerator. 0.5493 minus shift plus 0.5493. On the numerator I get a 1.15, but when I divide it by the 2.309 I get a 0.49999, which is reasonably close enough to 0.5. The only area where the errors are arising is because I'm not using enough decimal places here. But this 0.5493 answer is good. So you have to look at the reverse process. Can be pretty complicated, especially a quadratic equation come in here. Luckily it didn't, but it can. You have to learn how to work in the forward and the backwards directions. And you know, in this video I presented many different aspects of hyperbolic functions. This is one of those videos which will be slightly hard and difficult to comprehend the first time around. Feel free to look at it several times. I hope you enjoyed this video. I know it was a little messy. I know it was a lot on the board, but you always have the option to still the picture and look at it carefully as you jot down the notes. Thank you for watching. Have a nice day. Bye.